What's up guys, this is Jahangir from Emporium, and today we're going to be talking about everything concerning atoms, electrons, and orbitals. Now this is for general chemistry and organic chemistry as well, but this is more of our organic chemistry unit where we're going to dive deep into basic chemistry. So first off, we want to talk about atoms, and this might be a refresher to some of you guys if you've taken Gen Chem, and if you've not, then this might be some new information for you. So the first thing we need to talk about with atoms and the periodic table is atomic number. So, atomic number is one of the biggest things you have to know, not only to solve some of these conceptual questions, but also to understand the periodic table. The atomic number is basically the number of protons in that element. And in the periodic table, you might see something like, let's say I had carbon. So carbon, and you're going to see that top letter over here, or the top number over there, which is going to be 6. So this is indicating that carbon has 6 protons. So the atomic number always indicates the amount of protons that we have. And for example, if we looked at oxygen, oxygen has an 8 on top in the periodic table, which indicates that we have 8 protons. And one thing to remember is that the number of protons equals the number of electrons. So number of protons equals number of electrons. And throughout this whole video, I'm going to denote electrons as this E minus over here. So those will denote our electrons. Now, what are electrons specifically? Because if you don't know already, protons are positively charged. So I'll just put a positive. Electrons are negatively charged, and we also have something called neutrons. So we have neutrons. So neutrons are neutral charge. So these are the same weight as protons, and they are more dense than electrons, so they have more weight than electrons. So protons and electrons both have similar weights. Electrons are much lighter and smaller. So if we look at Bohr's diagram of atoms, and for some of you guys who don't know, Niels Bohr was a scientist who derived the Bohr's model of helping us understand atoms, and elements in general. So if we have something like, let's just say this is the middle of our atom. Now in the middle of our atom, we're gonna have like a couple of protons. So if we're looking at carbon, we'll have 1, 2, 3, 4, 5, 6. And neutrons, we will have 1, 2, 3, 4, 5, 6. This is assuming we don't have any isotopes, which we'll get into another video what isotopes are. So we have 6 protons, 6 neutrons in the middle. Now in the Bohr's model, we don't really write the protons and neutrons. This is only to help us understand the electrons. So we just assume that in the middle, our protons and neutrons are pretty much going to be in the middle, but our electrons are going to be outside, filling things called valence shells, or just shells in general. So our Bohr's diagram of a carbon would look something like this. So we first have this outer ring over here, and it can fit 2 electrons. Then we move on to the other rings, or the other shells, and these shells can fit up to 8 electrons until we get up to more shells. And as you go through each row on the periodic table, we're going to be increasing the amount of valence shells we have. So carbon is in that second group in the periodic table, along with oxygen and fluorine. So this carbon over here, we're going to have our electrons, so we already have 2, so all we have to do is put 4. So that's 1, 2, 3, 4, and that's the Bohr's model of a carbon. Now one thing to note is that these electrons don't follow a circular motion. That's not how electrons move, because electrons are wavelength. They have let me move that. They have wave-like properties. Now, I know it sounds simple of the idea that electrons just move in a circular motion, but that's not exactly how they move. They move in wave-like projections, and they're expressed in wave functions. So I'm going to put this in a different color. Wave functions. And this is how we mathematically determine, or this is how we mathematically express how electrons are moving. So we denote this as that Greek letter that I already forgot. But now we also don't know the exact position of those electrons. We don't know where those electrons will be, and that's due to the Heisenberg uncertainty principle. Now, Heisenberg uncertainty principle tells us that we don't know the exact position of an electron. We don't know for certain where it might be, but we do have a probability, or we have some understanding of where that electron most likely is, and we know that through orbitals. So the probability of finding an electron in a certain area is denoted by the wavelength squared, and visually we can see that through orbitals. And I'll just write this over here, but these electrons outside in our outermost shell, these are known as valence electrons. And when we talk about ionization energy in our future videos, this is where that ionization energy, those specific electrons that we're trying to break apart, those valence electrons, because these are the most outermost electrons that with ionization energy we can take them out. But just know that valence electrons are the outermost electrons, and the group of which the element is found is how many valence electrons it has. So if we're looking at something like carbon is group 4 or group 14. So you can assume that there's going to be 4 valence electrons, and with oxygen there's going to be 6 valence electrons because it's in group 6. So there's a couple orbitals we have to know. The first one is our S orbital. So S orbital. And remember, orbitals just show a visual representation of the probability of where an electron may be. Because we don't know for certain where an electron will be, but we know the probability at which area those electrons might be at. And the first one is called the S orbital. Now the S orbital, and I'll draw a graph over here just to show what the S orbital looks like. So if we have a graph like this, and we have this as a z-axis, this is our y-axis, this is our x-axis, our S orbital is going to be just a big circle, a big spherical circle. So it's going to be something like this. Our S orbital is going to look like a sphere. Now S orbitals can only hold a maximum of 2 electrons. So S orbitals can only hold a maximum of 2 electrons. And that number before the S, so it's like 1s or 2s, that number is the principal quantum number. And the principal quantum number tells us the shell and energy of the orbital. So what do I mean by this? Well, the principal quantum number really shows us at which row is this orbital at. So for example, we have 1s versus 2s orbitals. So 1s orbitals are going to be that first row in the periodic table covering hydrogen to helium, while 2s is going to be covering lithium and neon and so forth. So the number in front really shows us which shell we're at, so 1s, 2s, 3s, 4s, and this also shows the energy of the orbital as well. Now, talking about all these orbitals, we also need to talk about electron configuration. And electron configuration really helps us understand the amount of electrons in a specific element. We basically get to write it out throughout the orbitals that they cover. So for example, if we were looking at something like hydrogen, our electron configuration would just be 1s1, because if we look at the periodic table, hydrogen is the first element, and since it only has one electron, then it can only, in the first orbital we have to fit is a 1s orbital, then it'll be shown as 1s1. In lithium, we fill in that 1s orbital and we fill in the next s orbital, which is 2s. So this would be 1s2, 2s1. Or we could also write this as helium 2s1. So one of the things you could do is that when you're trying to write some of these electron configurations, you could write it to the nearest noble gas. Because if we're trying to write an electron configuration of like plutonium or any of those elements down there, like maybe iron, for example, it makes it much easier than writing the entire electron configuration. Another way to show electron configuration is sort of showing those electron configuration boxes. So it might be something like, if we go with our lithium example over here, then we're going to have this 1s orbital right here, and we'll be representing them by these boxes. So that's 1s orbital, then we have that 2s orbital, so we have these boxes. Now, there's a couple principles you have to understand when filling these electron configuration boxes. The first one, and I'll change my color over here, is the spin quantum number. So spin quantum number. And this is basically saying that electrons can have a positive or negative spin. So this is basically saying that we're going to have an electron pair that's going to have one side being a positive spin, one side being that negative spin over here. So that's the principal quantum number, and I just abbreviated the pound for just number. So another thing we need to talk about is the Pauli exclusion principle. So we have Pauli exclusion principle. And this is the idea where two electrons can be pairs as long as they have opposite spins. So if we're looking at lithium, and let me actually fill this one over here, the Pauli exclusion principle is saying that the only way for us to pair these electrons is if they have opposite spins. So as you can see, we have an up arrow right here, down arrow right there, indicating those opposite spins. Because one thing we cannot do, and this contradicts the Pauli exclusion principle, is that we cannot have those two electrons that have the same spin, because those don't fill the configuration boxes. So all we have to understand with Pauli exclusion principle is make sure they have opposite spins. Make sure that when you're putting in the boxes, you're writing in the boxes, you make sure they have the opposite spin, and the best way to do that is putting the first one up and the last one down. Now, another rule we need to understand, and this actually is more illustrated when we go to the p orbitals, is Hund's rule. So we have Hund's rule. So Hund's rule basically says that we need to occupy every electron orbital before we can double them. So what I mean by this is, let's say we had something like oxygen, for example, and we wanted to write those electron configuration boxes. So we have 1s, and we have that box over here. We have 2s, and we have 2p. Those 2p orbitals, which will actually have 3 boxes, and we'll get into that right after we talk about Hund's rule. So the Hund's rule is basically showing us that obviously we fill in these 1s and 2s orbitals, so we're going to have 2 electrons there, because if we remember, oxygen has 8 electrons, as we can see from the atomic number. So that's why atomic number is really important to understand. So we already filled 4 electrons. Now we move on to the other orbital, p orbital. So with Hund's rule, we have to fill in all of these boxes before we can double up. So we'd have something like this, where we fill in each box, and now we can double those pairs. Now we can have 2 electrons in each box. So that's Hund's rule and Pauli exclusion principle, and it just really details how you should be writing in these electron configuration boxes. So now let's move on to the p orbitals. So the p orbitals, we're going to have 3 different p orbitals, you could say. So over here we're going to have 2px, and we're just saying that these are going to be our 2s. So right after 1s and 2s, we head to 2p, and over here we're going to have 2py because this is going to be on our y-axis. As you can see, this is on our x-axis and this is on our z-axis, so 2pz. Now, one thing to note is that these two orbitals will be separated by what's called a nodal surface over here. So we're going to have two different lobes that will be separated by that sort of nodal surface, and they can hold a maximum of 6 electrons. So one p orbital can hold up to a maximum of 6 electrons. And each of these individual p orbitals can hold up to 2 electrons. So that's one thing to note, is that when we were looking at this oxygen over here, we had 3 boxes representing our 3 different p orbitals, and we can only fit 2 electrons to each of those orbitals, but in total we can fit in 6 electrons in the maximum for our p orbital, so that 2p. So when you're looking at the periodic table, it's really easy to identify which one is the 1s, which one is the or just which one is the s orbitals, the p orbitals, and there's also going to be d orbitals. But you just keep on going through that periodic table, and you can see that on the left side, when you look at those alkali metals, the group 1 and group 2, those are going to be your s orbitals. When you look at those non-metals going from group 13 to group 18 or group 3 to group 8, then you'll see that those fit the p orbitals. And then when you go down to those middle boxes, those metals, when you start going through those groups like 3 to 12, you're going to start seeing those d orbitals. So that's pretty much an introduction to atoms, electrons, and orbitals. And throughout your class, you might use these topics and go dive deep into many of them, but that's just an introduction to it. And as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.